So now we have a gas power cycle that has a generator, but has also got some other elements too. We have an intercooler and a combustor, and combustor 2, which we actually call a reheater. Okay? So the idea behind the intercooler and the reheater is to sort of reset the fluid before it goes into the second stage of combustion or the turbine. So as the fluid goes through compressor number 1, it's going to heat up. So the idea is a hot fluid it takes more work to compress a hotter gas, so we're going to take a little bit of the heat out before we compress it again. Yes, that means we have to put more heat into it later. However, it does increase the cycle efficiency because it's going to dramatically reduce the work that we have to put in to compressor 2 to make this cycle perform as we want it to. Okay, so then after exiting compressor 2, we're going to go and get a little bit of waste heat from the exhaust gas before we go into combustor number 1. So this is just really our typical standard combustor that we would have, say, in a Brayton cycle. And then we're going to go through turbine 1, and what happens between 6 and 7 is we have a temperature drop. And so to get that temperature back up to our desired temperature before we go into the second stage turbine, we're going to go through combustor number 2, or our reheater, and then continue on exhausting through 9, and then through the regenerator at 10. So on a TS diagram, this cycle looks a little nasty. I'm going to try to fit it in over here best I can. So let's start here at 1, and we're going to compress up to 2. All right? So we compress. If we compress isentropically, we have this line. So in my intercooler, I'm going to, at constant pressure, drop temperature to 3. From 3 to 4, compress again. And then from 4 to 6, all the way from 4 to 6, I'm just heating. So I've got different stages of heating, and that's all going to happen at a constant pressure. So here we go, 4, 5, and then along that same isobar up to 6. And we're still on the screen. That's good. All right, so 4, 5, 6, 3, 2, 1. This will be 2S and 4S. If these compressors are if they're irreversible, then we might come up here to 4, and then over here to 2, and have a little bit further ways to go in our cooling from 2 to 3. Okay, and then so from 6 to 7, we're going through a turbine. So if we have an isentropic turbine, we have a vertical line down to 7S. And in our reheater, we're going to isobarically heat back up. So what if we're going to heat back up all the way to the temperature at 6, that just depends on the cycle. I'm not going to draw it that way here, but at least we're achieving a higher temperature than we are at 7. And then again, second stage turbine down to 8S. So if we had irreversible processes, then we would follow these dotted lines to 7 and 8. And so then from 8 or 8S, I need to get all the way back down to 1 to complete my cycle. So 8 is over here, and then 9 is over here. There we go. That's better. All right. So to get from 9 or 9S, we need to go all the way back down to 1. So we're going to do this on an isobar all the way back down to 1, where we're going to pass state 10 somewhere along the way. Let's just put it right there. Okay? All right, so let's keep in mind that pressure is constant here, pressure is constant on that line as well. All right, so now let me introduce a new type of cycle to you. So keep in mind the big diagram we just had up on the board where we've got intercooling between compressors and reheating between turbines. So in an Ericsson cycle, all heat addition which is external, okay, so all heat, not incorporating regeneration, just external heat addition. All heat addition takes place in reheaters. And all heat rejection is from intercoolers. Again, not including some heat rejection from a fluid in a regenerator. Okay? So the next thing that defines an Ericsson cycle is that a regenerator allows heat input from process 2 to 3 to be obtained from heat rejection in process 4 to 1. Now, without a diagram on the board, this last bullet point here doesn't make a lot of sense. So drawing an Ericsson cycle is actually kind of tough. And I'm not going to attempt to do it here, but let me do you a little bit better on the explanation through a TS diagram. Here we go. So an Ericsson cycle really only has 4 states as compared with the 10-state diagram we had up just a few minutes ago. So let's start at state 1, which will be the entry point or the inlet of my compressor. And let's say that I compress my fluid and increase its temperature just a little bit and decrease its entropy just a little bit because now I've increased its pressure, so my entropy has gone down. Now I'm going to go through an intercooler and get back down to the temperature I started. Right? And of course, by cooling that at a constant pressure, I have only decreased my entropy a little bit more. So then I'm going to go through a compressor again, and another intercooler, and another compressor, and another intercooler, and so on and so forth, until I get to, I'll put it here, get to some state 2, and I'm now ready to add heat externally from, or add heat, not externally, add heat to my gas. Okay? So I'm going to add heat at a constant pressure in a regenerator, okay, to state 3. So remember the last bullet point we had before, that all of the heat input from 2 to 3 comes from the heat rejection from 4 to 1. So you can imagine we go through a compressor, intercooler, compressor, intercooler, so forth, many times. Then we go through a regenerator, and then we can start our turbine stages. Okay? So, in our turbine stage, we're going to drop the temperature and our pressure, so that's going to increase our entropy a little bit. And then I'm going to reheat in a reheater, and then go through another turbine, reheat turbine, so on and so forth, until I get to some state 4. Okay? And then I'm going to go through a regenerator and reject heat at constant pressure. So now the heat from 4 to 1 is being pushed over to process 2 to 3. So as the number of reheat and intercooler stages goes to infinity, I can transition from a plot that looks like this to one that is nice and smooth. And there we go. So, for an Ericsson cycle, all irreversibilities are presumed absent since all heat is transferred isothermally. So essentially what I've done is I've increased the number of intercoolers and reheaters to such a degree that the change in each compressor is minute. In fact, I can treat my process from 1 to 2 and 2 to 3 is happening at a constant temperature. And if no irreversibilities are present and I'm transferring heat externally with my environment at constant temperature, then I'm beholden to the Carnot efficiency. So the efficiency of an Ericsson cycle is the efficiency of a Carnot cycle. So the last type of cycle we're going to do in this chapter will be a Stirling cycle. So a Stirling cycle also has a Carnot efficiency because it transmits heat with its surroundings isothermally. And it consists of 4 internally reversible processes. The first is isothermal compression, followed by constant volume heating, isothermal expansion, and constant volume cooling. So of course, I need to generate PV and TS diagrams for these. So I'll begin my PV diagram with my isotherms, TH and TC. So the first one, I'm going to do isothermal compression. Pressure goes up, volume goes down from 1 to 2. Constant volume heating, straight line up, although I haven't done a very good job of that. Isothermal expansion from 3 to 4, and then constant volume cooling from 4 to 1. All right, so my TS diagram, again, I'm going to have constant temperatures TH and TC. So my first one is isothermal compression. So as I compress, my entropy is going to go down. Now I've got constant volume heating, so I'm going to be on an iso chord up to 3. Isothermal expansion from 3 to 4, and then again constant volume cooling from 4 to 1. A 100% effective regenerator, allows heat rejected from process 4 to 1 to provide the heat input to process 2 to 3. And of course, all external heat transfer it's kind of messy. All external heat transfer is done isothermally. So again, the efficiency of a Stirling cycle equals eta max 1 minus Tc over Th. The same as a Carnot cycle. So you may have heard of Stirling engines. I may have demoed one for you in class, or I may in the future demo one for you in class. So for a Stirling engine, the combustion occurs externally and ideally isothermally, although a real cycle is not going to hold quite to the idealized Stirling cycle. And it is a closed regenerative cycle, so we don't have mass flowing in and out of the cycle. We're using the same gas throughout the cycle as it turns again and again. So that should do it for this section. Thanks for watching.